Hi folks, welcome to the 14th rule of acquisition. This is the 14th rule of the 4th edition of Distinti's Rules of Acquisition. And 14.0, nature is not insane. This rule of acquisition will redefine the definition of insanity and then show that nature cannot possibly be insane. It's an objective to help the viewer understand and identify the properties of insane scientific theories, which could not possibly hope to explain nature, allowing a reasonable person to identify these bogus theories and steer clear of them. It's another objective to demonstrate that insanity has no practical applications. Before you go any further with this video, please stop here and review the definitions, the first 5 definitions on the definitions page. Go to distinti.com. On the main page, you will see a tab for definitions and review the first 5 definitions. You'll need to know these definitions before you go further here. So about the rules of acquisition, for those who have not followed this site, I have concluded that the human brain is easily distracted by nonsense, making clear logical thought difficult. The rules of acquisition provide a framework of tells, traps, imperative, paradigms, which help the brain overcome the groupthink, the false truths, and the tribal superstitions in order to improve the scientific method. Because we just can't rely on scientific corroboration of a theory, because too many people believe that scientific corroboration of a theory proves the theory to be true. And if you review the first rule of acquisition, you'll find out that this is clear humbug. And so we need a more elaborate set of rules or ways to view scientific theories in order to rule out the humbug. So the insanity tell. The insanity tell is a tell that identifies insane theories in order to invert scientific stagnation. Because we don't want to be fooled by correct answers. And as much as, Brian Greene on the quantum mechanics site goes, oh, the quantum mechanics has never proven wrong. It doesn't matter. It doesn't matter how many correct answers a theory gets. It does not prove it to be true. Because there are wrong theories, like the sun god model that never got it wrong. The sun always rises in the east and settled in the west. Sun god model never got a wrong answer. So that doesn't mean it's a right theory. And you have ambiguous theories like Faraday's law, and you can go to my foundation series to see all about that. And there's insane theories, which would be something in the order of quantum mechanics. And not in this video, but in the next video, we're going to go and show that quantum mechanics is quite insane. But this is a foundation for that upcoming video. And one of the problems with insane theories is they often lead to ever more fantastical and absurd predictions, like, for example, quantum entanglement, where I already have a video that shows that quantum entanglement is a complete misunderstanding of basic scientific causality. Okay, and because people waste time and effort on this humbug and this puffery, science is stagnating. Okay, so we need a means other than, hey, we get the right answer in an experiment. That's not sufficient anymore. We need another way of looking at scientific theories to judge their validity. And the insanity tell is one of the many tells in the rules of acquisition. So this is where we're going to end up with the insanity tell. I'm not going to read these. We're going to go over these and come to this conclusion and review this at the end. But if you want to stop and read this now, this is where we're going. So let's begin with Einstein's definition of insanity. He said, doing the same thing over and over again, expecting different results, is insanity. I honestly think this was an attempt at a cut at quantum mechanics, but it wasn't very well posed. So let's look at this for a second. Let's use this deck of cards. This is an ordinary deck of playing cards. There's nothing crazy or fantastic. This is just a deck of playing cards. And now let me do something. Okay? I'm going to shuffle the cards. Okay? And I'm going to pick the top one. 10 of spades. Okay, let's put down the 10 of spades. Okay, a spade. That's supposed to be a spade. All right, now let's do the same thing. Let's put this card back in the deck somewhere. Oh, we got our supervisor decided to finally show up. Okay, and we're going to do this again. And let's see what we got. Now, I'm expecting a different answer. Okay, I'm expecting a different answer. Does that make me insane? Got the 5 of spades. I got a different answer. Whatever, I can't draw a spade. Okay, so we have to look at this definition of insanity, because here I can most certainly do the same thing over and over and get a different answer. So this definition of insane as put forward by the great Einstein is quite insufficient. So what we have to say is that because this is an indeterminate system, as through the definition I said before, that even though this deck of cards is a deterministic system, but because we shuffle it, we're adding indeterminacy. In other words, by shuffling it, we lose the understanding of what the order of the cards should be. And because of that, the system becomes a quasi. We're going to call it a pseudo indeterminate system. We'll cover that in more detail later. Okay, so a proper thing would be in a determinate system, doing the same thing over and over and expecting different results would be insanity. It should never work. You should always get the same results when you do the same thing over and over again in a deterministic system. In an indeterminate system, doing the same thing over and over and expecting the same results would be insanity. Okay, so this is an indeterminate system only because I do not know the order of the cards, or by shuffling it, I destroyed any notion of any concept of what the actual ordering of the cards is. Therefore, it is a pseudo-random system at this point. Okay, so now what we could assume then is, could it be argued that an indeterminate system is insane because there is no ability to predict the outcome of the cards? In other words, I could do this over and over and I have a 1 in 52 chance of getting 2 cards in a row that are the same. Because I have no predictability other than being able to use probability, is this system insane? Well, let's look at this in a little bit more detail. Okay, and maybe because probability and statistics offer some measure of predictability in an indeterminate system, and without some ability to predict the outcome of a natural system with some kind of modeling idea, some kind of modeling methodology, then we can't do anything practical. You know, how could we build a starship if we have models and theories that we cannot discernitively predict the outcome of? In other words, we can say, well, we have a probability distribution, how big the size of our starship could be. Yeah, you go and try and find engineers that are going to say, yeah, we're going to build a starship based on a superposition distribution. It ain't happening. We need to be able to define exactly the size of the starship, what it's made of, what it's going to be powered by. There can be no indeterminates in that starship. If you'd had that, no engineer would work on it, because what you're doing is putting people's lives in danger. Okay, so what we have determined is that probability theory does in fact give us a little bit of the ability to work with an indeterminate system. For example, okay, if you and I were to play blackjack with this deck, okay, and then that's your whole card, that's my whole card, that's your top card, that's my top card. Well, from this, and maybe as we play more, you can or I could use probability theory based on what cards are played in the deck. But in other words, what we say, we could use card counting and probability theory to get an edge over our ability to bet against each other or bet against the house. However, now, but that requires this deck to remain stable. Card under here is not constantly changing. This card isn't constantly changing. So it requires some means of determinism here. And like I described in the determinism video, whatever the value of this card is, even though we can't see it, that's got to remain that card. Just like this card is remaining the 5 of clubs, and it's not changing over time. The minute I put it down and I pulled it out of the deck, it's been the 5 of clubs ever since I did that. That has to be true for the value under here as well. If the value of this card were changing all the time and the value of this card were changing all the time, if these cards were continually changing their face value, there is no way that you could use probability theory to have any kind of edge in how you bet. Okay, so therefore probability theory actually requires the system to be stable and determinate, causal and discrete. And we're going to cover that in more detail. We're going to go over that all over again in case you did not follow that. So let's explore this deck again. Sometimes you have to say things twice for people to get it. Okay, so these are the competing properties we're looking at. This is a discrete deck because each of the units are whole units. It's not like you have 5.4387 of spades and a 4.96847 of spades. These are discrete values. They're not continuous values. If there were continuous values, then you would have every card from the 4 of spades to the 5, let's say, assuming that's a spade. I don't want to go find the 4 of spades. But let's say you could have every value. If this were a continuous system, okay, you would have every value from the 4 of spades to the 5 of spades. And if you tried to apply a probability of which card was drawn, your probability distribution goes to 0 for any card. So probabilities cannot be used on a continuous system. Probability theory can only be used on a discrete system. Now, for those people that haven't seen the discrete versus continuous video, yes, you can apply probabilities to a continuous distribution, but what you end up doing is discretizing it. If you don't understand that, go see the video in the definition, or the definition in the definition video. Okay, so probability theory requires a discretized system. Okay, and let me do causal in a moment. Okay, and now we have quantifiable versus non-quantifiable. Yeah, I can count how many cards are on here. Okay, and they have a value, and there's 5 of clubs. That's a 5 of clubs. This has a value, even though it's just an abstract value. And so, if you did not have a quantifiable system, you could not make predictions on an outcome. In other words, if you wouldn't know how much fuel to put into your starship. The kind of fuel you're using is not quantifiable. I mean, if you're how do you build anything with things that are not quantifiable? You can't. So a non-quantifiable system is not a system that you're going to be able to do probabilities or any kind of designing of starships with. So you're going to have a quantifiable system. I mean, how can you apply a probability and say, yeah, what's my probability of getting the 5 of clubs when there's no quantities? Okay, you kind of get that one. So probability theory can only be applied to quantifiable systems. A causal system. Okay, let's do this. One, two, three, four. Okay, I did a little sleight of hand trick there. No big deal. Any magician could figure this out. But the point is, even though the shuffling adds an indeterminacy to the system, it is still a causal system. And because I know it's a causal system, I was able to work around the shuffling to make 4 aces come up on top. Okay, so that means that even though this looks like we're adding a non-causality, if we went and studied all the forces involved and all the tensions and stresses, we could numerically determine how exactly a card deck was going to be shuffled if we could control the forces to comply with our theories. Okay, and therefore this shuffling that we're doing is still a deterministic system. And you say, well, how can you have a deterministic system that's random? Well, look in computers when you have a pseudo random number generator. Pseudo random means it's not really random, but it appears random. That's the same thing that happens when you're shuffling the deck. It's a pseudo random ordering. Okay, and like in the computers, it's pseudo random. If you apply the same seed value and give the first 10 numbers of a pseudo random number generator, you get the same 10 random numbers over and over and over again. And so we make the pseudo-random act more random by putting a seed value that's like based on the date and the time. So the seed value going in is never the same, and that gives us more of a feeling of randomness, even though it's not truly random. Okay, that's very important. So even perfectly random systems can be based on completely causal phenomenon, that they appear random. They appear random only because we may not know all the forces, like you may not know the algorithm of the pseudo-random number. For all intents and purposes to you, it appears truly random, even though it is a causal system. So now I'm going to do a little bit of thing here and say, yeah, probability theory can be used on causal and non-causal system because, so this is kind of for the purposes of probability, this is a question mark, but I'm going to say to you that non-causal systems do not exist for other reasons that we'll get into later. So let's get to the last one, indeterminate versus determinate. Okay. If you go back to the determinate versus indeterminate definition, this deck of cards remains determinate. In other words, after it's shuffled, the values don't change. It remains the same. Therefore, if you and I play blackjack and we don't know the order of the cards, our betting would have to, the only thing we could use to bet against each other or the house is to use card counting and probability theory. However, if one of us was able to go through and determine and mark down the order of the cards in the deck before we started playing, well, that person would not have to use probability theory. He could use very deterministic betting and optimize the bet against the other person or the house. Of course, that would be cheating, but we're not talking about ethics of gambling. We're talking about this is a system that could be used in a deterministic way. And that order of those cards is not going to change at all. There's no forces. Nothing is causing those cards to change values and spin and have a probability distribution or probability superposition like they talk about in quantum mechanics. These card values are stable and stationary right now unless I pick them up and actively shuffle them. Okay, but let's assume that we had a truly indeterminate deck of cards here that's based on a purely non-causal randomness, okay? Well, just like in quantum mechanics, when we put the cards down, let me pick other cards here. Okay, and even though, so if these cards were truly indeterminate, it wouldn't matter when you look at them. They're never going to have a stable value. They're always going to be changing. So this could be moving from clubs to hearts to diamonds. It could be the 6, the 6.5, the 3, the ace, the king. It wouldn't matter. Their values will be constantly changing between all of the cards in the deck. Okay, that each card maintains a single stable value here means this is a deterministic, stable causal system. But a truly indeterminate system means you would never be able to determine the value of this card, even by looking at it. Yeah, there's the craziness in quantum mechanics. They say that, that in the Schrodinger's cat, that, if you didn't know the value of the card, there's a probability superposition and it's all those values at the same time, which is complete nonsense. Because it would mean that what they say is that when you look at it, it picks one of those solutions, which is ridiculous. If you have a probability superposition as they define it, and your ability to look at it makes it stabilize on one value, well then you have a causal system there. And then there should be then a way to look at it to get any value you want to stabilize there. And you should be able to look in the box in a certain way and either get a live or a dead cat based on your causal ability to look at it. Okay? So, and because, now if we go back and say that these are probability superpositions, and these values are constantly changing, and they're never stable, even if you look at them, then there's no way that you could use probability theory to come up with a way to bet me against you, you against me. In fact, there'd be no way to even play the game, because you wouldn't even know the values. Okay, so this leads us to an interesting, we have to change the definition of indeterminate, that there's two kinds of indeterminate systems. Oh, all right, I'm a little bit out of order here. So the two types, there's the true indeterminate system that we talked about here, where it's truly that this card is constantly changing between all the possible cards in the deck, and it's never stable. And by looking at it, it's not stable, because if you look at it and it stabilizes to a value, then there's a causal thing going on there. There's no causality if it's truly indeterminate. If it's indeterminate, you cannot determine what it is, even by looking at it, even by observing it. So that would be a true indeterminate system, and a truly indeterminate system is completely useless. It could never be modeled, and it could probably never exist. Okay, but what we have in this deck of cards when we shuffle them is a pseudo indeterminate system, and I just messed this up. Okay. So when we shuffle this deck, just like that random number generator, we're assigning a pseudo-random distribution of cards. It's still the same 52 cards. The cards never change value. They may change space as you shuffle them. So you're applying a causal physical system to change the order of the cards. But once you stop that, the cards will remain where they are. This system becomes stable. It becomes causal. It becomes deterministic. Okay? Because the only difference between this and the only reason why this is now indeterminate or pseudo indeterminate is because we just don't know the order of the cards. If we did know the order of the cards, then we could bet very deterministically. So there's the difference, that a pseudo indeterminate system is basically a system where we're lacking knowledge. And for all intents and purposes, we could treat it as an indeterminate system, but it's not an indeterminate system. It's a system that we can't determine the outcome. I don't know the value of the card on the top. I've lost that information in the shuffling, but this is a determinate system nonetheless. And because I don't know the order of the cards, the best we could do is use probability theory and I believe this is an ace on the top, and that should be another ace, and that should be okay, I did do a little shuffling in there. So anyway, so that is a pseudo indeterminate system, just like a random number generator that they use for all the gambling machines. It's still based on a deterministic, causal, stable system. It is not a truly indeterminate system. Because a truly indeterminate system, you would never be able to determine the value of the card. Okay? So we use pseudo indeterminate systems. And this is the only thing that probability can be used on. Well, yeah, because this is the only place that probability has any value to us. But it says that their underlying system is deterministic. Okay, so what we're going to say now is the 14.0. Nature is not insane. Insanity is a system that can't be modeled or predicted and thus has no practical application. A sane system is deterministic, quantifiable, discrete, causal. Insanity lacks one or more of these properties. And probability and statistics has no value if the underlying system is insane. Because unless this system is deterministic, causal, quantifiable, and discrete, there's no way you can apply probability theory. So probability theory is only useful in a deterministic system where we have lost some information and we have to use probability theory to try to make up for what we don't know. And so therefore quantum mechanics, which is based on probability theory, is a system that admits that there's a lot of missing information in our understanding of nature. I'm getting a little ahead of myself. That's mostly for the next video. So a system is insane if there are no modeling techniques that could allow a measure of predictability of the system such that benefit could be derived from it. An insane system can have any or all the following properties: truly indeterminate, continuous, non-causal, non-quantifiable. Now, for continuous and non-causal, we have to look at the page after the next. And then we get to the pseudo-insane. Okay, which is like the pseudo-indeterminate system, is a sane system where humans lack sufficient knowledge to model it in a causal deterministic fashion and resort to probability and statistics. That's like gambling, cards, flipping a coin, whatever. Because in those systems, even though the systems are all causal and deterministic and quantifiable, we just don't have the technology, or even it may not even be practical to go and model all the physics in there to find exactly what we're going to expect. But that they are available if we choose to do so. It may not be practical to do so. Now getting back to these caveats here, although nothing that exists could be continuous, comma, it is permissible to use continuous mathematics to model nature. The normal mathematics that we use is a continuous system. It doesn't exist because it's completely abstract. It's okay for a continuous system to exist in an abstract fashion. It's not real, but it's a useful tool. It is continuous. And what we learned in the rule of acquisition 12 is that math is a superset of nature. Okay, in other words, with mathematics, you can define any level of dimension, whereas physicists believe the true universe is somewhere between 11 and 12 dimensions. Okay, even in mathematics, you can define fractional dimensions and continuous dimensions and all kinds of strange things that would not exist in the real world. And that's why we have to be careful, because rule of acquisition 12 basically says just because you can derive something with math does not mean it exists in nature. However, anything that exists in nature should be able to be modeled with math. Okay, so there's not a duality here. I think you can get the subtlety of that. And the other subtlety is to do with non-causal systems. Okay, so probability and statistics are modeling techniques that are more about correlation than causality. We must be careful not to infer the insanity of the tool into nature. Yes, our tools can be insane. Continuous math means continuous math is insane, but it's useful because it doesn't exist. And the same way with probability and statistics, it is not a causal system. For example, let me give you a simple example. You'll hear a statistic that says that 95% of all accidents happen within 5 miles of the home, car accidents. Well, what's the causality there? Is there some kind of evil being that haunts around your house and then notices when you're in 5 miles of the house to strike? Does the car dealership know where you live and plant all kinds of mines and explosives around to cause you to get into accidents so they can sell you another car? I mean, you can come up with all kinds of strange causalities. Or it could be something just as simple as saying that 95% of the time that you're driving, you're somewhere on a road that's within 5 miles of your home. Which would mean there's no causality to your home other than that's where you spend the most of your time driving. Okay? So you have to be careful because with probability and statistics, because there's really no inherent causality, again, this is another insane modeling technique, but it's useful. Okay, nature can't be insane, but our modeling techniques can. We just have to be careful not to attribute the insanity of our modeling techniques to nature. Otherwise, we come up with weird things like charges coming back from the future to make our stupid equations balance. So 14.4, do not attribute any insanity of the modeling tool to nature. And this is the 14, the insanity tell in all its glory. You can read these at your leisure. I'm not going to read them back to you. This is basically all we've gone over. Reasonable men adapt to the world around them. Unreasonable men make the world adapt to them. The world is changed by unreasonable men. I'm not so sure about that. I don't think nature gives a crap about how reasonable you are. I think when they're talking about the world, they're talking about human nature, and human institutions are changed by unreasonable men. Thank you. No more voodoo physics. Please subscribe. Give me a thumbs up. This is one of the last videos where we're going to talk about quantum mechanics. The next video is basically going to be the final video. We're going to talk about quantum mechanics. We're going to put the final nail in the coffin of quantum mechanics to get it out of the way of ethereal mechanics so I can go on. The reason why I have to do this is because we do not want there to be anything about quantum mechanics that is required of ethereal mechanics to explain if we can basically show that quantum mechanics is gibberish, which it pretty much is, not the experiments. We're going to explain the experiments that quantum mechanics has, but not their theories. Just because their theories agree with the experiments does not mean their theories explain the experiments. Okay, because if their theories are not sane, they are not a reflection of nature. Thank you very much.